To welcome everyone to the recitation on remote manufacturing, sending parts and drawings off to be fabricated. We have Jamie, who you met earlier at a previous lecture. So the Space Exploration Initiative staff member who helps with all kinds of electronics assemblies and things like that. And we also have Levi, who is a friend of the Space Exploration Initiative and has collaborated on multiple projects in the past as well. So we're going to have Jamie go first. He's going to talk about like PCB manufacturing, things like that. And then Levi will go second and talk about more mechanical things. And I'll let them give a brief intro of themselves before they go. But I'll just go ahead and hand it over to you, Jamie.
Okay, thanks. Hi, everybody. My name is Jamie. I have been with the Space Exploration Initiative for a couple of years now. Started working on Ariel's project Tesserae, and that was sort of my main focus for a while, but since then I've helped out with a number of different projects in different varying capacities. Helped out with Space Human and a little bit with Maggie's Space Food project. About to get involved in a couple others coming up. But basically I'm sort of in an advisory role, part-time, helping with all kinds of electrical engineering, embedded programming. And in this case, so we're gonna talk about basically interfacing with board houses to fabricate PCBs. So I will share my screen. So I'm going to go through these slides fairly quickly. There's plenty of content, but of course, if you want, trying to leave plenty of time for questions. But if you want more detail on something, feel free to just stop me, and we can talk about it. Otherwise, we will get started. So this talk is basically saying, starting from the point that your circuit board is finished, you've done all your design, you've done all the layout, and basically now you're ready to actually fabricate boards. And like, what is a board house gonna need from you? So there's a standard set of things that's pretty much every board house can handle and will expect, which is the Gerber files, the NC drill files. Optionally a net list, we'll talk about that. Optionally a drill drawing, that's for fabrication. Then if you also want them to populate the boards, they're going to need an assembly drawing, sometimes pick and place and centroid files, and of course a bill of materials, which is all the actual components that go on the board. And we'll talk about each of these. So the Gerbers are sort of the fundamental thing. Sorry, I've got a very curious cat right now. I won't leave me alone. The Gerbers are sort of the fundamental description of artwork for the board. So this particular artwork is for this board that we've built. And you can see here, I'm showing you the top layer and one of the inner layers. So Gerber's just an ASCII-based format that basically describes where the copper is and where it is not. These are sort of the graphical renderings of it, but if you actually just open a text editor, you would see it's just a whole bunch of ASCII text. There's a difference between the signal layers and the plane layers in that the signal layers are defined by, you can see the red layer here. Everywhere where there's red is where we're going to keep the copper. Everywhere where it's black is where it's actually going to just wipe. Starts with a solid copper clad board, and it's going to etch away all of that other stuff. Plane layers are a little different because they're typically mostly solid in the first place. Plane layers being power planes and ground planes. So when they describe plane layers in a circuit board, they actually describe it as negative data. So in the green one, the green is actually where they're going to remove copper, and everything else will be connected to that plane. So there are several, we just talked about sort of the copper layers. So you're gonna, when you run an output job, when you're collecting all these files, there are, the top and bottom layer at least, for the 2-layer board. You may have inner plane layers, you may have inner signal layers. So you want to run a separate output for each one of those layers. There's what are called the screen layers or the overlay layers. These have to do with the solder mask, which is like the green stuff that covers everything but the pads. The silk screen, which is typically white. These are just typical colors. They can be whatever. But the silk screen is where you put the text, the reference designators, the outlines, the pin 1 markers, diodes, polarities, that kind of stuff. And then optionally, there's a paste mask. When the boards are built, they build a stencil, like a metal stencil with lasered out holes that they lay across the board, and they actually just like squeegee solder paste right onto the board. Then a pick and place machine comes and puts all the components in place, and then they reflow the whole thing so that everything gets soldered at once. So the paste mask defines the thickness and the area of that solder. It's typically looks just like the solder mask because you're exposing all the copper pads and then you're putting paste on them. They can be a little different. Two other things that you want to add typically is a dedicated layer for board outline that you can then include with everything, with all the other layers. So the top layer would have a board outline. You can see that was done here in this red one. You can see this outline. These each have the same board outline, then the board house can use that to register the layers to one another when they're checking your data. And the drill drawing, which we'll get into. So the next thing that they need as a minimum is the NC drill file. So this is another text file that is describing all the drilled holes in the board. So this is going to be all the vias. It's going to be all the mounting holes. It's going to be the through hole components for these connectors here are through hole connectors. I put up this graphic because I did want to point out that for some programs, the one I use called Altium, they actually do put out 2 separate files if you're using slotted holes like this up in the corners here. So the round holes, which are just the straight drills, will have one thing. The slotted holes will have another. So you actually have to include both of those text files in your data outputs to get that built properly. The reason you might want to use slotted holes like this is, in this case, this gives us some room to move the mounting up and down to align it. If you want the board completely tested, depending on what you're buying, like if you buy something from like PCBWay, all they're going to ask for is the Gerbers and the NC drills because they're just building your board, and it's on you to make sure that it's correct. If you want a board house to completely test, you can generate a net list, which is basically like you can see down in the corner. Like there's a net name like VCC TOF, and then there's everything that's connected to it. C95 pin 2, J8 pin 1, U15 pins 5, 7, and 8 are all connected to that net. So they can feed this into a flying probe machine, and they can actually just go through and like check every combination of nets and make sure that the copper is connected, make sure that the vias are all valid. So this is a way of like, making sure that the board was built, and also grabbing fallout, like some board, maybe you'll have like 5% of the boards for whatever reason, the trace was not connected, it was too thin, or the plating on the via was not sufficient. So you can catch things like that. The board houses can do this with just the pads typically, with the raw boards that haven't had the solder tinning on them yet. But it's a good idea to drop these little test points. You can make a little footprint for just a dot. This is like a 25 mil diameter dot that I can just drop on a net, and then that gives them a place to really easily probe the net. So if this is something you might think about adding if you're going to do more mass manufacturing and need a lot more full coverage and full test to make sure that the board was built properly. So this is a bit of an eye chart, but basically the drill drawing is another Gerber layer, but it's sort of a dedicated layer that has a ton of information on it. And if we were to zoom in on this, you could see This again, here's the board, but now we've got like dimensions, X and Y dimensions. Sometimes you'll dimension like from hole to hole to make sure that those are proper. It's also got this chart here, which is the drill table. So this reflects what's in the NC drill file, but gives a little graphical interpretation. So every different size hole gets a different symbol. And then it's described here. I'm using only plated through holes, meaning like all of the holes actually have like copper tin plating through, so they're connected from layer to layer. You can also do things like just drilling straight holes through the board for a mounting hole that's not electrically connected to anything. So that would be a non-plated through hole. The other thing this describes is, all these notes, these are fabrication notes. So this is where you would call out if you wanted lead-free solder, or if you want a certain IPC rating, which is an inspection criteria. Like there's different levels of inspection for the boards. You can call out the plating. Like this one we use like a gold. It's kind of hard to see there, but we use like a gold plating, which is really very flat and solderable. Adds a little cost, but it's nice for soldering for reflow. You could call out conformal coating. So this is your set of notes that just say everything. There's like a boilerplate set that you always put on there, and then you can add other stuff. This is where you capture all of your fabrication specific to your board. This also shows the layer stack up, which I go into a little more detail on this slide. So what I'm showing here, this particular board is a somewhat complex board. It's a 10-layer board, or 12-layer board, sorry. So it's showing here how to build it up, because we have target thickness, which is the standard 62 mils. But you can do 62 mils in 2 layers, and you can do it in 12 layers, and you can do it in 4 or 6. So you have to call out how thick each layer should be. And if you're unsure about this, the board houses can suggest things for you. Altium and other programs actually also have standard stack ups, especially for like 4 and 6, which are very common layer stacks thicknesses for people to use. So this is basically like when they actually fabricate the board, everything starts out as a 2-layer board. So if I want a 12-layer board, it's 6 2-layer boards that get sandwiched together and glued with these what's called a pre-preg. You can see on this chart on the left here, there's core and there's pre-preg. Core means like a fiberglass core with FR4 typically. Pre-preg is basically glue. It's basically like a defined type and thickness of a sheet of glue that will actually hold these things together. So this is how they build the board stack up. So again, like the board house will want to know this, but if you're unsure about it, they can suggest typical stack ups for typical boards, 4 and 6 layers. Or you can ask me as well, and we can work it out. So that was all talking about the fabrication of the raw boards. If you also want the board house to build it completely, they're going to need a second set of outputs. The first one here being the assembly drawing. So you can see this is a graphical representation of what the parts physically look like on the board, reference designators for everything. Basically the board house, and you can see I also have like polarity markings for those polarized capacitors. There's polarity markings for all the ICs, so they can tell the orientation of pin 1. So the board house is going to need something like this, so they can match. Basically, they're going to program the pick and place machine based on this and based on your BOM, and based on some other potential outputs, which we'll talk about in a minute. But this is something that's like generated from the finished file. So it's assuming that you have like all the correct footprints. That's something that's like more of an upfront thing when you're actually designing the board, creating like a footprint for this J2 connector. Like this needs to be the right width and spacing for the part number that you're going to call out. And a good board house will catch those kind of things for you as well. They'll go through as they're programming it and make sure that all this stuff matches up. An additional thing that they will sometimes ask for are pick and place or centroid files. These basically say, you know, based on the origin of what was shown in the drill drawing, they're giving you Cartesian coordinates and rotation of the part. If this is done correctly, if your library is built correctly in the first place, this is great. A lot of board houses don't actually trust this because they don't, you know, they don't trust that users always put the center of the part in the, how shall I say this? Let me show you actually. If I grab a part here, this is a connector and I pull it, of course it's locked. Let me just unlock this. So if I grab this part and pull it, unlock, there we go. You can see this actually is not holding by the center. It's holding by this pin. Now it's holding by the center. Now it's holding by that pin. So there's some variability, and this has a little bit to do with the way Altium actually grabs things. But the point is, the center, the physical center of this part is not always properly defined in the libraries. So that's kind of why some board houses will just say, you know, just give us all your parts and give us the assembly drawing and we'll program it for you. We'll go through and so this is a lot of the cost actually is them basically building up and making sure that everything will be placed correctly. But sometimes board houses will ask for this. So this is another, you know, output that can be generated. Probably the most important thing is the bill of materials. I've given a little example here of the, you know, it's just a little snippet of some BOM that I had. This is sort of the bare minimum that I always give board houses, and it's really all that they need. Sometimes you can include things like the DigiKey part number or the Mauser part number. If you're working with a major distributor like Arrow, then you probably have their own part number as well. But you need the designator so they can match that to the assembly drawing. You need the quantity of the parts so that they can, you know, quote how many. This is per board, by the way. So this is not, you know, if you're building 10 boards, it's 10 times that. Description sort of just a nice to have, but probably, you know, for your own reference, it's a good idea. And then the very important thing is the manufacturer and part number. Manufacturers will tend to have especially within ICs, they'll have the same beginning part number, but then a slightly different suffix, which denotes different thing, you know, like a slightly different package pinout spacing, you know, like QFN 32 versus a QFN 48 or something like that. So this is where you kind of have to be careful and do a real BOM scrub and make sure that you've got the right part. Because these don't always get caught until they're like ready to program the machine. I've had this, believe me, I've had it happen many times where I had just slightly the wrong part number. It can cause kind of a headache because it will stop your job. Like they'll be ready to do your job, and then all of a sudden they'll find this, and you know, it'll cost you a day or two while they sort it out. And again, this you can do these by hand, but if your library is built properly within your CAD software, you should be able to run this as an output as well. So it'll just sort of like build this for you, and you know, that way you can make sure it's correct once within the library, and then you should be all set from there. So just wrapping up here, I just want to talk a little bit about what drives the cost of boards. So for raw fabs, layer count and complexity are sort of hand in hand. Layer count obviously is just like more steps to build the board. So that's going to add to your cost. Complexity, when I say complexity, I also mean things like very narrow tracing space, blind and buried vias. So blind vias are vias that start on one end but don't go all the way through the board. Buried vias are ones that are literally sandwiched between, so you can't even see the via from either side. those are quite expensive, but they're rare that you need them. That's like an extremely dense board that needs that kind of thing. But you may run into that if you're really miniaturizing things. Slotted holes add a little bit of price, but it's not crazy. Other things like rigid flex can get expensive as well, because again, it's a complex process of marrying polyimide with FR4. Quantity and lead time is an interesting one, because quantity, when you get the raw fabs, at some point it's all setup cost. And so if you want to buy 1 board versus 5 boards versus 10 boards, the total cost will be like almost the same. Like they'll charge you, you know, $100 per board for 5 boards and $500 for 1 board. It's just all setup costs at that point. It's like not really materials costs. So oftentimes, if you're gonna buy 5, then you might as well buy 10 and have some spares. The lead time also is like, you're basically paying to jump the queue, more or less. You can get a 5-day lead time. There's some places that will do like 24-hour lead times if you're willing to shell out, you know, like for a serious emergency, but they will charge you for it, believe me. But like 5 to 10 days for fab is kind of typical. You can push it out even further if you really want to save. You can go like 15 or 20 days, but then you really got to be planning ahead for that. You know, the NRE, like a lot of times they'll just say like NRE, they'll tell you what the NRE is, and then they'll be like, yeah, we're waiving that. But I think they're probably just putting that into the price some other way, but that's my opinion. In electrical tests, like I said, you know, this, you can get it or not. If you're doing a simple board with, that's like not very complex, 4 layers, like your boards are going to be okay. Assembly is a little different. You're always going to pay our NRE for assembly, because they're always going to need a programming step for the pick and place. So you can't really get around the NRE for that. The component cost is basically they're buying, you know, they will buy like some small subset of the components and then put them on the reel, even if you're only putting like 1 of something on a board, unless it's like something they can hand solder. But if you're putting like 1 or 2 surface mount capacitors on a board, they still need to put it on a reel, so that the machine can handle it. So they will mark them up for that service, basically. And again, quantity and lead time applies here as well. When you're quoting things, board houses are very used to people asking this kind of question, or you quote in a bunch of different quantities with a bunch of different turn times, and then just give you like a matrix of prices. So don't hesitate to do that. Like I said, you know, 5 to 10 days for fab and 10 to 20 days for assembly is kind of where I personally run at. You know, so half a month to a month from the time you drop the PO to the time you get boards shipping to you. One other thing I forgot to mention is panelization. Sometimes board houses will just do this for you. You can tell them how to panelize things. Or you can just, you know, just give them the raw data, and they're probably going to panelize it one way or another. Like this is an example. We didn't ask for them to panelize it this way. It just made sense for them to do it, to put 3 boards per, because we ordered 10 boards. And so they gave us 4 panels. And they're attached, if I can get this close to the camera, they can be attached by these little, these are what's called mouse bites. So there's just like, you know, here and there. You can also get them attached by a V scoring, which is like literally what it sounds like. They score it like a V on both sides of the board, so that you can just like break off the edges when you're done. But this is basically just, you know, it's an odd shaped board, and they want everything that goes into the machine to be a rectangle. It just makes it easier to mount. So they will put it in some sort of panel like that. Yeah, what else do I want to say? You know, that's pretty much all I wanted to cover. I kind of ran through that quickly just to make sure that there was plenty of time for Levi and plenty of time for questions. So I don't know, Sean, do we want to take questions now, or let Levi do his thing?
Let's let Levi jump into his thing, and then if we have time after that, we'll do questions.
Okay.
So thanks, Jamie.
There you go.
All right. Hey, everybody. I don't think I've had a chance to meet many of you yet. Let's see. Can you see my screen?
Yes.
Perfect. Awesome. Cool. So I'm Levi DeLuke, also a friend of the Space Initiative, sort of unofficial helper at times. I think the topic of my discussion today will be more structured like a case study. So sort of walking through sort of a prior experience, taking a product from idea to final manufacturing. I'll share a few resources more geared to the mechanical side, since Jamie has already covered the electrical things, and then just open it up for questions. But if you guys have questions at any point throughout the presentation, feel free to just jump in and unmute and ask. So before coming back to school, I was a CTO and co-founder of a medical device company called Wellynx, and that's sort of the case study that I'll be walking through today. In short, we are essentially creating a device for kids with scoliosis. So we made a sensor that attached onto their back braces to measure how the braces were fitting, and then a mobile and web application. And so the focus of today's talk will be on the hardware side, of course, and not on the software. And then before coming back to school, I worked a bit as an EMT and a contract engineer for some other medical device companies. I'm currently a grad student at MIT in the Leaders for Global Operations program, dual degree mechanical engineering master's and MBA. And I'm actually not in school now. I'm part of an operations graduate research fellowship at Amgen here in Cambridge on their manufacturing team for auto injectors. Yeah, so just jumping, I mean, so these two pictures we'll sort of come to in a second, but this is sort of our first like production run of the devices, and me trying to correct various mistakes that we made manually. So a lot of today's lessons will be like hard-learned things that we messed up as we are getting started as a company. So yeah, I think I briefly mentioned this. So we started out like doing research and sort of just like coming up with a bunch of ideas and then taking it all the way to initial production run before the company was actually eventually bought beginning of last year. But you know, I think the stage that it sounds like a lot of these projects are, and where I think that honestly the bulk of work probably should be focused is still on the like prototyping stage. And we went through, you know, multiple rounds of prototyping the devices before, you know, considering scaling up and manufacturing. And so this sort of took the form of sort of an off-the-shelf like Arduino platform where with a 3D printed case. And then we made our first circuit board and sort of went through a lot of what Jamie just described of ordering, you know, the boards and hand soldering them ourselves. And then for subsequent ones, actually sort of purchasing, you know, having them assembled out of house as well. But the key of these sort of subsequent rounds of iterations on the mechanical side, we're at this point, you know, all about getting different feedback from the user, trying to prove out the concept before sinking a ton of money, right? So this stage was really focused on, you know, proof of concept, and it wasn't a huge deal if a part ended up costing $5 more because we were only making one of something. We often really cared about lead times and, you know, availability of components. That started to change as the company evolved. So we had our first essentially like pilot study at a hospital where they needed 10 devices, right? So still very much in the, you know, you can manage that yourself level of scale, but it also, you know, started to be, the device started to shift beyond the capabilities of just everything being 3D printed. And so part of what this was, you know, I think just like partially an educational experience for us, but we wanted to see what it would be like if we made everything in-house using our extremely limited capabilities. And so the parts on the left are essentially a laser cut top for the device. The middle parts were CNC sort of aluminum pieces. And then the two parts were both a 3D printed and a machine version of the plastic case of the device. The real sort of lessons that we are trying to do here was to work out any, you know, problems with the actual functionality of the device before making 100 or 1,000, let's say. And this is the first chance we also had to like test the device, both like, you know, through pulling it, but then also just wearing the device around and seeing how it performed. You know, I think that at this stage, it became immediately apparent that we needed to stop doing everything in-house, right? Like each device probably took 5 or 6 hours of machining and doing small little things, which was already bad at, when we were making 10, but it would be impossible if a customer said we need 100 or 1,000. And so that's really where we shifted focus to sort of larger scale production. This was also for an official clinical study at a very large research hospital. And so we needed about 100 devices for this study, but we also needed the ability to rapidly scale that up afterward for a contract with a company. And I'll sort of later on in the discussion cover like this decision. But we decided at that point to go to an injection mold instead of a 3D printed part. We use Proto Labs, which is sort of in the next section. I'll chat about some resources and sources for sort of low volume injection molded parts. And the key decision here, and this is one that was potentially a mistake, was the fact that if this sort of trial was successful, we had an immediate order for parts. So we wouldn't have the ability to sort of start the injection mold process afterwards. And, I think a lot of mistakes were made in this round as well. The one I noted here is that we spent a ton of time just thinking about like, how do we design an injection molded part, right? It was the first time of us doing it. It was our biggest expense as a company to date. So we spent all this time just thinking like, and learning and talking to people about, how do you go from a 3D printed part to an injection molded part, and had not spent a lot of time thinking about like assembly and testing of the device, which ended up taking a significant amount of time that we had not considered. All that being said, I think that this was a really good step for us to do like the final assembly in-house as opposed to contracting it out, which is what we did later, because we did learn about these small intricacies and changes to the device that we could make to improve its performance and manufacturability. Ideally, that would have happened before ordering 100 devices in an injection mold, though. And so, I still, in retrospect, think we probably jumped to the injection mold side of things maybe a little early. And then the final phase, I'm happy to like talk in detail about these phases at some point, but just for the sake of the class, just cover them at a high level. The final phase of our sort of production came when we had orders from customers, right? So we are a regulated medical device. It was not feasible for us to produce these things in-house. We were not a certified medical device contract manufacturer. And so we were really fortunate to work with one that was very close to us at the time in Connecticut, who helped us walk through this process of like, how do you go from, a Protolabs injection mold, which might cost like $5,000 because it's made out of aluminum and is really geared towards sort of, wide tolerances and low production volumes, to a like tightly controlled spec that was water resistant and ultrasonically welded together and had really tight tolerances. And so the biggest decision that I had made at the company up to that point was the decision to like pull the trigger on these injection molds. Like we did not have the money to do it over again, right? Like $60,000 for us was like a substantial amount of the funding that we had left. And so one of the like things that we did was pay for like an extremely high fidelity 3D print of that same exact part with like as close to the same mechanical properties and tolerances that we could find before pulling the trigger on the injection mold. I think that there's like a ton of nuances about like working and identifying and building a partnership with a contract manufacturer that are maybe less on the manufacturing and technical end and more on the, business sort of developing a relationship, project management side of things. But I would say that like that was the decision that like I think we did best as a company. And I've seen a lot of companies like, or companies or projects, I guess, whenever they're scaling up, really struggle with. And I think that we are extremely fortunate that they essentially took us under their wing and mentored us and like helped us redesign the device and spent enough time with us to teach us these changes that needed to be made, as opposed to just sending a part out and saying, we need 1,000 of these made, right? And sort of having a handoff relationship. So if there is any lesson to be learned from this stage that I could share. It was like, I would never go to this stage without working with someone who is like significantly more experienced than myself, right? Like there are people whose entire careers are injection mold design and ultrasonic welding and that sort of stage of manufacturing. And so we are really lucky that they were willing to help us out. And then a final note on this stage, I sort of alluded to it earlier, just in terms of testing. We had to do a lot of things like simulate use of our device for a very long time. So what would happen if the user pulled on a certain direction for 18 months? On the electrical testing, I think Jamie sort of alluded to it. We had both electrical testing of our boards before they were populated, but then once they were shipped, we had a series of tests and protocol that they needed to pass before they left. Initially, right, I could just do that with a multimeter or soldering certain things to the board. But once you are making a larger volume, we ended up creating a series of these like test fixtures that you could sort of place the board on, and these little spring pads would make contact with. And you could do that without powering the boards, right? So it would be sort of an all-inclusive testing jig, essentially. And so this was like one, we ended up making one that could test the whole panel at a time. So it would test 10 boards. And so things like this, I think, like we didn't do for that interim, like small run. We sort of learned that lesson and did it for the subsequent run and really made the scale up a lot easier. And so we essentially ended up creating this tool and then giving it to our contract manufacturer so that they could use it. Just like a few high level tips, like each of these topics could be like their own class. So everything's going to be covered at a pretty high level. But these are, I think, just some of the tips that when you're moving from a sort of 3D printed part to an injection molded part, there's some pretty good guides online. And so I'll sort of leave those to y'all to find, or I can link them. But the three things that like tend to change the design the most in my mind is you essentially have to draft the walls. So you can't have like two vertical surfaces that then pull apart. You can, but it's likely to mar the surface and they tend to not like it. The second is that as the part cools, it will shrink. And if you have sort of non-constant wall thickness, or even just a really thick section of material, that shrinking can either just look bad, or it can actually affect the mechanical sort of structure of the device. And then the final one is that right angles are to be avoided in a lot of cases if you can, just for like stress reasons, and it's pretty hard to machine, particularly if they're like deep in a part. So this is just, I think, an overview of our process that we tended to take for parts. So we had a longer discussion as a team. I mean, my co-founder was more on the product design side, and so she would often do, a first pass at like the look of our device and then hand it off to me to try to translate that design into something that could be injection molded, let's say. And then from the CAD, we would then 3D print a part because it made no sense to jump right into injection mold. And then we would for all of our parts, sort of what Jamie said about like, it doesn't hurt to go ahead and ask for quotes, for multiple quantities of sort of PCBs. We would tend to always submit our parts, unless it was like something you knew was infeasible. We would tend to submit our quotes for like the three likely candidates for making it. So 3D printing, machining, and injection molding. Even if it was like something we knew we would never get injection molded, the quote process for a lot of these companies is actually like semi-automated, and it was just a good way to like identify things that we would maybe want to change anyway. So maybe taking advantage of their services, but particularly somewhere like Proto Labs or Xometry, they actually have a pretty nice automated platform that will give you different breakdowns of price, the setup fees, and make suggestions about what changes you make to your part. And so they also have engineers there who will like work with you and explain those changes and help you make them. And so I tend to think that like quoting early is like, there's no harm in like submitting quotes and just trying to think about what you might want to change on a design. I think, and this is, I mean, sort of not going too in depth of the technical details, there's like an art to injection molding. But I think that like we never really messed up on the like technical stuff because we had people who were much better experienced at us helping us with it. I think most of our mistakes were like business considerations or like sort of non-technical things about like how many of these parts do we really need at this point? Like, sure, we say we need this many, but like is that actually true? And like, what is the likelihood that you're going to have to make like a complete redesign after a certain round? I think that I underestimated how much feedback we would get on a device that would require a completely new injection mold. And I think sort of mentioned it before, same as Jamie's actually, they will give you different breakdowns of like quantities and setup costs and have like a full conversation with you about that. For like our injection mold in particular, like it just made sense for us to buy like 200 of the parts instead of 100 because the setup cost was significant compared to the actual per part cost. So just the final things before we open up for questions. The next few slides will just be some like sites that you can actually go to and submit quotes, so some more like practical examples. I know there's others. These are just the ones that like I know of and were around when I was building a bunch of stuff a few years ago. So Protolabs and Xometry, they essentially have like almost everything, right? So they've got 3D printing, they've got sheet metal, they've got CNC milling, lathing, and injection mold. So like they're often a helpful place, and they'll give you quotes for like multiple of their services all in one go. And so, you can essentially take your sort of 3D CAD part, send it to Proto Labs, and get a good sense of like what would manufacturing look like. And it's worth like talking to them, right? They've in my experience been pretty open to doing that. I would say that both of these are probably geared towards the like smaller scale production run, and they are somewhat limited in capacity. So like at the time, they wouldn't guarantee like the tolerances that we needed for our part or do like a first article inspection. I think some of that maybe has changed in the past few years, but there's something that you give up for the extremely low cost of both of these services, or low cost for like injection molding comparably. But laser cutting, I think, is like underappreciated just for like its costs, particularly if you're making like 50 of something or 100 of something. We ended up laser cutting the initial like lid of our device, and it ended up being significantly cheaper than we thought. And the materials that are available if you outsource to laser cutting are greater than those that I think MIT allows in a lot of like labs. And so there's sort of a wide range of capabilities if you outsource to some of these places. And same goes with 3D printing. So like there was a time where we really wanted a 3D printed part that was as close to possible of the mechanical characteristics of the injection molded part. So that changed both the method of the 3D printing and the material. And we essentially used that to do some early mechanical testing on the device before the injection mold came in. And so all of these places, if you have like that type of detailed question of like, I'm trying to match the mechanical properties, it's worth just like, submitting a quote, but then also following up and trying to have a lengthier conversation. And then some final lessons, and I'd be happy to, I guess, open it up for questions, I think the thing I briefly alluded to it, but we could have saved maybe like $5 on our cost of goods for that initial sort of small production run if we completely outsourced it and went, overseas or somewhere that like I would never have the chance to see. That being said, it was worth it for us to be able to drive to where our devices were being built and drive to our PCB assembly house, because I personally just didn't have that experience and valued the chance to like see and learn from them and drop off parts and pick up parts in person. And so I think it's like, at least for me, it's something worth considering, is like, see if there's a local PCB house or a local machine shop or a local injection molding place that is willing to work with you, even if it means a little bit more money, until you get to the stage where you're making like tens of thousands or thousands of thousands or something. And then the final thing is like, we were frequently tricked into like price break, not tricked, but like it was very appealing to say like, oh, like we're going to need more of these parts. Might as well order 3 times as much as we need just to, get that price break. And we have like, even to this day, so the company's been bought, we've got mountains of inventory that will never get used and was like wasted money. And so, just like another mistake that I made, I think, was like assuming that we would need the same electrical components, or that like those metal loops that we mentioned, we ordered 10,000 of those and we used like 50 or something. So I mean, they were cheap. They like cost like pennies a piece, but I have like 10,000 metal loops that no one ever will use. Yeah, that was final lesson learned. So happy to answer any questions that you'll have. And then more broadly, if you have like detailed questions about any of these services or any of the sort of next steps, I'm always contactable sort of after the class as well. So.
Thanks so much, Levi. If anyone has any questions for either Jamie or Levi, please ask them. Does anyone think that they're going to need to get anything manufactured from it's especially relevant this year since we have limited access to our to the shops and things like that. So even for like one-off parts, I know we try to gear this toward more scaling up, but for one-off parts, this could be pretty useful too.
Yeah, I'd be curious to know if people have been working with places like PCBWay or those kind of quick turn board houses. Is anybody actually building boards that are not just dev kits strung together with wire at this point?
I am, but I'm mainly using JLC PCB in their assembly service.
I've got a question for Jamie. I'll cheat. At what point do you decide to have like the assembly done, like outsourced versus soldering it all yourself?
Yeah. So a lot of times when I develop a board the first time around, I'll actually deliberately use parts that can be hand soldered. Even when I probably would have used a QFN or a BGA for something, I'll try and find a hand soldered part just so I can build them. I got this little reflow oven that I built out of a toaster oven, which works pretty nice. And you can get the stencils for cheap. If you're buying the boards, they'll throw in the stencil for $10. So definitely, the first round, when you like, as you said, when you're building like 10 or fewer, you can kind of just do that, and it's a good way to save a lot of money because you're going to be making changes. But when the boards start to become more dense, like anything that's like BGAs, forget about it. Even with the reflow oven, like you're probably not going to get that right. QFNs, I've done them, but they're not fun. So anything that's like leadless or very small, and then when you get to quantities above 20, we've also seen that for prototypes, you can build things quickly and rework them quickly, but there are going to be workmanship issues, especially if you're building a bunch of them. Like it's just like there's only so much soldering you can do under a microscope before you just like short a lead or don't get enough solder on a paste. So we've seen that before. So then going forward, if we're going to give anything to a customer, even if it's just a beta, we have those built by a board house. And anything that's I would say for things like suborbital flights or ISS, like you probably want to think you can definitely build that stuff by hand, but be careful, because it's critical, mission critical, everything. So I think that's where I would draw the line, is like if it's going to a customer, if it's mission critical, or if it's just impossible to build.
I have a question for Jamie. You mentioned if you outsource this to board houses, having them test whether like there was that testing stage that you recommend, or actually, I guess my question is, do you recommend that since we're going to all this trouble to getting to outsourcing and compiling everything for them to do it, do you recommend that we just do that testing phase versus like, what's the likelihood that things won't work?
So for simple boards that, if you're doing a 4-layer board with relatively generous geometries, meaning like, 6 mil trace in space, and not super dense, like not tiny micro vias and stuff. Nowadays, I mean, board houses are pretty reliable. You're likely to get a good board. Electrical test is sort of when you get many hundreds of components on a board, so you have like lots and lots of traces, things that are really miniaturized or dense. And as Levi said, there's also two, there's the electrical test that I'm talking about is for like the bare board. So they fab the board and they just probe it to make sure that this is connected to that. Then there is the component, like the stuffed board testing. That is much more expensive because you need to build like a custom fixture that's like just for your board. It's a bed of nails. It's like a clamshell that like sandwiches your board and hits all these test points. And so that's really nice to have. That's going to tell you like the true yield of your build. But that's sort of like going to production. You wouldn't do that until you're like ready to go to production, just because it's quite expensive. But the electrical test on the board, yeah, a lot of board houses will like either just throw that in as a service for free, or it's a pretty modest fee. So I would look at that, and if it's available, then certainly take advantage of it. Yeah.
Cool. Thanks.
Good time for one more.
I have something between a question and a request for Jamie. My project is very similar to Ariel's. It's about kind of using electromagnets to do assembly in microgravity. So I've been picking her brain about it a little bit, but it would be great to chat with Jamie maybe sometime offline about the design process and how maybe the things I'm not thinking about.
Sure. Yeah, we definitely learned a couple things about the power paths, that like handling the power, and especially off a battery powered source, like trying to do electromagnets off a battery powered source. So.
Yeah, I'm thinking about like just discharging very high currents in short amount of time, and maybe thermal issues and that kind of stuff. Great.
Yeah, sure. Drop me a line. We'll set something up.
Great. Thank you.
Thanks, everyone. Especially thanks to Jamie and Levi for taking the time to share their experiences with us. I'll be putting their contact information in the recap email, so you can reach out to them later if you have something else. So with that, let us go a minute early. Thanks, everyone.
Thank you.
Guys.
Bye.